Okay, so if you have been following along, you will realize that we have been putting up very brief quizzes on Moodle. Okay, some of you did not realize that there were quizzes being given out. Uh, so typically, a quiz comes out every Wednesday. It's due by the end of the week before the next class. This was mainly put in place because there's an entire section of students who don't come to class, they follow along online. So just to ensure that they are viewing the lectures, we wanted to put up a quiz that was related to the two lectures for that week. But for those of you who are here, also you should take that quiz so you know that you're following along and so on. Okay. Typically, there is no makeup. If you miss a quiz, it's okay. The overall grade for all the quizzes combined will be almost 14 or 15 of them. It will be very small. So if you miss one quiz, don't worry about it, but try to keep up. Okay, for everyone in the class. That's one. The quizzes are different from homeworks. There will be real homework. Quizzes are supposed to be very brief. Shouldn't take you more than 5 minutes to fill out. There will be a homework that will take more than 5 minutes, so that's going to come out soon. First homework, I thought that we'll have 4 homeworks. Okay? So every 5 lectures we can give a homework. Lecture 5, 10, 15, 20. So there will be 4 lectures, 5 homeworks. Today is lecture 5, so I'm trying to see if we can give out a homework soon. As soon as I do that, I'll send out an email to the list. It will be posted online. We will have a week, 10 to 10 days. There will be plenty of time to turn it in. Okay? All right. And we are getting to a point where we can also start thinking about the lab. Labs assignments are done in groups. So the only thing at the moment you should worry about is if you want to do it in a group, who should you team up with? Okay, so try to form groups now so that when the lab is given out the next week, 10 days or so, you are ready to go. Okay? You can do it as an individual assignment, that is no problem, but we recommend if you want to be a group, do it as a group, that's fine as well. Okay. Any questions on any of these administrative things? All right, so let's continue where we left off last time. We were talking about distributed scheduling and multiprocessor scheduling. I explained the scenarios where distributed scheduling is actually useful. Basically, I said when the system is lightly loaded, there isn't much to schedule. Jobs can be executed wherever they are being submitted. And when the load is high, there isn't much you can do by moving jobs around in the system. Every machine is more or less likely to be loaded. So it's in the moderate utilization regime where distributed scheduling is useful. Okay, and I explained a sender-initiated policy for doing this kind of scheduling, a receiver-initiated and an adaptive policy. Okay. What I'll now talk about are 2 or 3 real systems that put this into practice. Okay, the first 2 systems will be research systems, and then the next 2 are systems that are actually in use today. Okay. So the first one is the V system from Stanford, designed I think in the mid to late 90s. Okay, so almost 20 years old now. So this was one of the 2 systems that actually came up with this notion of distributed scheduling. It was a research project, never actually became any commercial product, so nobody would have used it outside of the researchers who designed this system. Okay. It was designed to be a distributed operating system, but the important part of that we are concerned with here is the scheduling aspect. Okay. So it assumed essentially a state-driven information policy. Okay. So what that means is essentially if you see any significant load changes in, if a node sees any significant changes in its load, whether it's memory utilization or CPU utilization, you broadcast that to all other nodes. So you say my load is now X, it's 80% CPU utilization or 90% memory utilization or whatever that may be. Okay? So because nodes are broadcasting their load information, especially significant changes in load information, every node has some insight into the load on other nodes in the system. Because you receive these broadcast messages, now you know what the load is on a node I, if that's the node that broadcasting. Okay. So that's basically how you keep track of. So you don't go and pour. Okay. The 2 techniques I talked about last time was when you have to send a job or receive a job, you explicitly go and ask a node to send its load information. Here, nodes are asynchronously broadcasting information as and when they need to. Okay? And then we assume that the least loaded machines in the system are receivers, others are senders. Okay? The least loaded nodes basically, if you're among the M least loaded, you have a table of load on most of the nodes. You sort that, and if you are in the bottom M nodes, you become a receiver, otherwise you're a sender. And just the policy here is to be sender initiated. It's the sender's job to send task to some other node in the system, to some other receiver in the system. Okay? And then the location policy is what happens is, since you have M least loaded nodes that are receivers, if you are a sender, you are going to first pick one among these M nodes and poll, saying, are you still a receiver? Okay? And if the answer is yes, then you can send a job. If not, you try another node. Okay, the reason, despite having load information, the reason you poll is that since that information was broadcast, it may be stale. Some few other machines may have sent jobs to that receiver node, and it may have now gotten loaded enough that it cannot accept any job. So you have a list of receivers already from the broadcast information. Before you send a job, you check. You pick a node randomly among the list of M, and then you basically poll that node saying, can you still receive jobs? And if yes, you send the job. And with no process migration here, so you always send new tasks. Okay? No notion of a process migration. Okay, that's a very quick. There's a paper on this entire system that I can post a link to. You can read it in more detail, but this is essentially a one-slide summary of what that system used to do. Okay, second case study. This was a competing research project of us. The V system was developed at Stanford. The Sprite system was developed around the same time. That was also an operating system, a distributed operating system. This was developed at Berkeley. Okay, and here basically the had also distributed scheduling mechanisms built into it, but some of the assumptions were different. Okay? Sprite was designed for what was called a network of workstations. Okay, so the assumption was every user in an office environment is given a workstation. Okay, let's say a powerful workstation. And then also the assumption was the load on these workstations are not going to be uniform. There are going to be load skews. Sometimes a user may not be at work or may not be at his or her desk. They may be in meetings, they may not have come into the office, and that workstation is just sitting there idly. And there are other workstations that may be heavily loaded. And the question was, how do you take advantage of idle CPU cycles on workstations that are not currently in use? Okay? And if you find such workstations, then they can accept some processing jobs from other workstations that are loaded. So essentially it's doing distributed scheduling, but you have to go around trying to figure out which workstations are idle and which ones are not. Okay, so it's a workstation environment. But if you do this, then you have to ensure that the user or owner of the workstation is not going to be impacted by jobs that are sent to that workstation. Okay, a simple example is the following. Right? So let's say that user gets up at noon, goes out for lunch. Okay? So the workstation is just sitting there idly while the user is away at lunch. And then let's say the system decides to send that workstation some jobs. Okay? User comes back from lunch and now finds that the mouse is not moving because the machine is heavily loaded, is not even responsive to your mouse clicks or whatever. That doesn't make you happy, right? Because it's your machine now, somebody else sent a job and you can't do your work. Right? So you don't want that scenario. So the assumption is owner is king. So you basically always respect the owner. And what that essentially means is anytime the user comes back to his or her machine, you have to give the machine back. Which means if there are background jobs that some other machine has sent to it, they have to be stopped and sent back somewhere else. Okay? So that's basically, so you always respect that your users of workstation always have first priority on using the machine. Only when the machine is not being used, you try to actually use those CPU cycles to process some other tasks. Okay? So the way it works is you basically, the way Sprite used to work is essentially tracked whether the machine has keyboard activity or mouse activity. Okay? And so long as there is some keyboard activity or mouse activity, you assume that there is actually a user sitting there and typing away or doing something with their mouse. Okay? And if you see that there is some amount of time for which no such activity has been detected, then you assume that machine has become idle. Okay, now how you what time period you pick is up to the system. In this case, they picked 30 seconds, which seems awfully short, because if you just go and pick a book from your office and it takes 30 seconds to do that, your machine will be declared idle and start receiving jobs. So you don't want somewhat, but this was an aggressive policy, but it assumed that if there is no keyboard or mouse activity for 30 seconds and the load on the machine is actually below some threshold, that the user himself or herself hasn't started some jobs locally, then you assume that the machine is idle. Okay? And then it becomes a receiver. Now this was a centralized policy. Okay? So there was a coordinator in the system that kept track of which machines are idle and which machines are not idle or loaded. Okay? And then that coordinator would essentially allow senders to send jobs to idling machines. Okay? So centralized policy, the coordinator that keeps track of what's happening. It's also state driven. So essentially, as soon as you become a receiver, if this condition is true, there's no mouse or keyboard activity, load is low, the receiver contacts that receiving workstation, contacts the coordinator saying that I'm an idling machine, I'm willing to accept jobs from the system. Okay? Select, so senders you can decide. So whenever you submit a job, you can say that find the best machine to execute this job. And then that machine would have to contact the coordinator saying, is there another machine that is less loaded than this machine? And if so, that's the machine that the job is going to execute. Okay? So location policy, sender queries the coordinator tells the sender where to execute the job. Okay? So now as I said, because owner is king is sort of the rule here. If you are a workstation that's accepted a job and the owner of that workstation comes back, then the machine has to be returned back to the owner. The job execution has to be suspended. Okay. So then you can ask what happens to partially executed jobs. So maybe the job ran for an entire hour while the user has gone out for lunch. User comes back and now you have to stop that job. Okay? And let's say it has another hour to go. So what do you do? Okay, one option is that you just terminate the job and restart it. Okay, so you can just say the job didn't finish, bad luck, let's just find another machine, maybe this time you'll have a 2-hour window to execute the job. So you can just do that, terminate it, restart. Yeah, that obviously wastes all of the cycles that have been already spent on executing this job until now. Okay. Second option is you need to add a functionality that can take a job that has been partially executed, okay, and has been suspended and move that entire job somewhere else and restart it from that point on. Okay. If you have that, then you have to do what is called process migration, because this is a process, it's an executing process, but it just belongs to some other user, it just was sent to this machine. And if the owner of that machine claims that machine back, this process has to move somewhere. Okay, now that means you have to implement process migration. Okay, so that was the new functionality that Sprite added, which was not even there in V, was it actually implemented process migration. Okay, you could actually suspend an entire job. You take all of its memory contents. The way you do this is you take the memory contents of this process, save it to disk, okay, and then decide where this job needs to resume execution. Okay, either you make that disk accessible on that other machine, or you actually copy the contents of this process onto the local disk of the new machine. You load that entire contents back into memory there, okay? Instantiate those contents as a new process on that machine, and then you resume execution. Okay? It's a complicated process, okay? Because you are actually moving a process from one machine to another. There are lots of issues that you have to deal with. Okay? You want to ask a question? Go ahead.
It's already a complicated process, but I feel like I'm missing like another complicated piece.
Yes.
Is it a homogeneous environment of workstations, or is there some like directive on like this is how you compile my program?
Yes. So I will talk about all these issues just one moment. There are more complications even before you assume whether it's homogeneous or heterogeneous. Okay? At the moment, I'm just explaining how process migration works. Okay, so essentially, you have to transfer the state of this process. You will swap everything out. All the memory pages of this process will be swapped out to disk. Say the page tables, file descriptors, etc. Okay. Now here, Sprite assumed a distributed file system, so the disk state was shared. All the files within the file system could be accessed on any machine. Right? So you didn't explicitly have to copy any data, but if you did not have a distributed file system, all of the data had to be copied over. In this case, you didn't have to because the file system was distributed. Any machine could access files stored on any other machine. Okay? And when we talk about distributed file system, it will become clear how to do that. At the moment, just assume that you can access a file on any machine in the system. Okay? If you do that, then you on some new machine, you page those pages back in. First, you have to create a new process then. Process 10 here has no meaning on a new machine. That has its own process ID space and so on. So you create a new process, you take this memory space and you sort of upload it into that process and you start, so all the registers get uploaded, etc., etc. You start executing. Okay. Now there are many issues here. First one is that this process may have opened files. It may be actively reading or writing files. Okay. And if those files are being written to local disk and you now move this process to a second machine, okay, those files don't exist on the local disk there. Okay, so this thing is just going to break. It's not going to work. If you try to write a file foo, that file was present on disk 1, it is not accessible on that machine, you will basically get an error and the process will crash. Okay? So if you have to deal with files that are open, you have to assume that those files live on either a network server or a distributed file system, so you can continue to access them from a new machine. Not an easy task, so you're putting some restrictions. Otherwise, the thing have no meaning. That file has no meaning on a new machine. That's the first problem. That's somewhat simpler to deal with because you can say this all I/O has to be done to a network file server. So all the files are written to server. That server can be accessed from the second machine as well. So then it's okay, or it's a distributed file system. Okay. Second problem is what if this process is actually doing network I/O? If it has open sockets and it's communicating with some other machine. Okay, that's a more complicated problem. Now, if you just move this process to another machine, that machine has a different IP address from the first machine. Okay, the other end has no idea that this machine has moved. Okay, so if it continues to send packets to the old IP address, the process is gone. Okay, so all your connections are going to break. Right? So you can only say one of two things. You can say process migration will only work for those processes that do not do network I/O. Okay, then if you move it, there are no sockets, so there's nothing to worry about. Okay, so you can either impose that restriction or you have to somehow deal with a change of IP address. And the way that can be done is you basically have to essentially have a tunnel from the first machine to the second machine. So all the packets will continue to arrive to the first machine and they're forwarded by your workstation that ejected this process to the second machine. Yeah, so it gets complicated is the short way to think about it. I mean, it's doing the swapping of the pages and loading it on another machine is actually simple. That's not the problem. The problem is all the resources being accessed by that process. How do you ensure that those resources, whether it's a network socket resource or a file resource that are being accessed, how can you continue to access them on the second machine? Okay. There's a question asked about what assumptions are we making about the hardware environment. Clearly here, although I did not make it explicit, in the case of Sprite, you assume that it was homogeneous. Okay? You can't move a process from a Intel architecture to a Spark architecture. Okay? The machine code is not even going to work there. Okay? We will see ways to deal with that as we go along. Okay? Well, how do you deal with migration in heterogeneous environment? At the moment, assume that at least the workstations are all identical. They're all Intel machines of the same type, so that any compiled binary is going to at least work. If the binary doesn't work, you cannot do this at all. Okay? All right. So we will come back to this. This is just a case study of how Sprite did it. We will look at migration and better ways to do this, okay, as we go along. Any questions on this? Does that answer your question about imagination? Okay. So that's Sprite. So those are two research projects. Okay? They had good ideas. They were one of the first to try out these ideas: distributed scheduling, process migration, and whatnot. Next two case studies are on systems that are actually in use today. Okay? First one is called volunteer computing. Okay, so this is basically this has many names in the literature. People also call this internet scale operating systems or ISOs and things like that. So you'll see how some of the ideas are now going to carry on. So in volunteer computing, what you do is if you have a machine of your own, you can decide that you want to volunteer its CPU cycles to some task that somebody else needs to run. So you are volunteering your cycles to some other task. Okay. There are systems, not systems, there are applications like SETI at home, there's something called Boink and so on, where these scenarios make sense. So assume that there is a user, okay, that needs to run a very large amount of data processing or computational applications. They do not have a cluster large enough to run their jobs. Okay, so what they go and do is they say, I need to do this for some good cause. Any user anywhere on the internet can donate their CPU cycles to this good task. Okay? So whenever that user is not using their machine, that machine will actually contact some central coordinator and send me a small task. Okay, that coordinator will send it some task, will do computation, will send back result. If the machine continues to be idle, this will repeat, okay, until the user claims their machine. Okay? So this is using a similar idea to what was done in Sprite. Okay, machine became idle, machine went around looking for some work cycles. I mean, it was contributing a cycle, it ran some tasks, and when the user came back, the machine was given back. The way it works in this case is basically you have to download a small piece of software. If you want to volunteer your machine, you have to download a small piece of software. That software actually runs as a screensaver on your machine. Okay? So whenever you are not at your machine, your screensaver will activate. So it's idle and the screensaver runs. The screensaver is actually a program. Okay? The screensaver will actually then contact the central server saying, now this machine is idle, this user has basically volunteered their cycles to some cause, send me a job. And a small task comes over, you run that for a short period of time. Then if your screensaver continues to run, you basically keep asking. And when the user comes back, the OS already will deactivate the screensaver. So then whatever task was running will go away automatically. So you don't need to do anything special. By running these volunteer cycles as screensavers, user can claim their machine back at any time. Right? Now, what kinds of applications do people run on volunteer computing systems? There are many different ones. Okay? So SETI at home was one of the very first. SETI stands for Search for Extraterrestrial Intelligence. Okay? So basically, these are astronomers who had large radio telescopes that were simply scanning the sky to see if there are any signals that you can actually see from outer space, to see if there is any sign of life outside. Okay? And simply because the amount of data that these telescopes were collecting was so large, and they did not have resources to build their own machines to process that, they basically said, let's go and see if other users anywhere can contribute their cycles. So anytime a user is asking for a job, you send it a small part of the scanned signal, and then you look whether there is any pattern that you can discern. Okay? So since there's a lot of data, and this data can be partitioned into very small tasks, where you have to look, is this silence or is this garbage, or do I actually see any real signal, radio signal in this data that has been collected? You can parallelize this quite a bit. Okay? If there are a million machines, you can sort of have a million machines all working on different parts of the data. Okay? So these are what are called embarrassingly parallel application. The more machines you throw at it, the more parallel it becomes, because you can chop up all of your tasks to very small bits and farm them out in parallel. Okay? That was the first system that actually started all of this. And now there are lots and lots of applications that do similar stuff. There is a system at Berkeley, I think it's called Berkeley Open Network Computing or some such thing, that's the acronym. You can actually be an application designer that goes and applies for cycles there. The coordinator runs there, and then anybody who contributes tasks can go to that coordinator. So this is done for discovering new drugs for cancer and doing lots of these data processing for a variety of good causes. So if you feel like you want to help these, whoever these application designers are, achieve their goals, then you can become part of the system and volunteer yourself. Okay. Now, as you can imagine, this is a very loose form of distributed scheduling, because there's a coordinator that's just farming out tasks. They're being scheduled on lots of different machines. Results are sent back, machines come and go, and all of that is dealt with nicely. Okay. So if you're interested in knowing more, I think you can go and actually Google either of these two. You'll see pages and you'll see how they work. Okay. Okay. Last case study is Condor and some of its derivatives or sort of similar other systems called SunGrid engine. Okay, so these systems are also designed to use idle cycles on workstation or simply schedule jobs on a cluster of servers. Okay. Again, Condor is basically has taken ideas from Sprite and is implementing that in any local area network where there are machines. Okay. So again, in the Condor environment, if you run it on a set of machines and machines become idle, they go to the Condor coordinator and say, send me a job. Okay, then you can essentially send a job to that machine, the machine will execute some job, user comes back, the job has to be suspended. Okay, so the Condor has support for migrating a job to another machine or restarting the job, whatever policies you want to set up. Okay. So idle machines contact Condor for or Condor assigns a waiting job. Okay, when the user returns to the workstation, you can suspend a job and migrate. There are a number of flexible scheduling policies in Condor. Okay. You can run Condor in this workstation environment. You can also buy a system of servers, a cluster of servers, and run Condor there. In that case, you will just submit a job. Okay, there's a centralized queue, and then the Condor coordinator will just take a server in the pool and assign that job to that server. Okay. There is another system called SunGrid engine that's actually used, also widely used, including in this department, to assign jobs to clusters. Okay. If you have used this cluster called Swarm, okay, there's a large cluster here that people use for their research computing needs. If you have to run, let's say, lots of simulations for a research paper or whatever, and you need lots of machines, you apply for an account on this cluster. Okay, it runs SunGrid engine. There are lots of users. Each user submits one or many jobs. Okay, and then this scheduler, the distributed scheduler that is running on SunGrid engine, will decide which of the machines in the cluster will execute your job. You don't actually say run it on machine I or J. You just submit it to the entire system. And then the SunGrid engine scheduler decides which of the 100 cores are going to actually run your job. Okay, so it will schedule it based on whatever policies are in the system. Okay. So these are 4 different examples of systems that use distributed scheduling today. Okay, so 2 research ones, 2 systems that actually use them in today's applications. Any questions on this? We are going to switch gears and change topic, starting with the next slide. Okay. So next topic, which is related, as you will see, the reason we have this topic here is that it has something to do with migration and so on. The next topic we are going to study is virtualization. A slight change of topic, but you will see how they all connect up. Okay, you probably have heard of the term virtualization or virtual machines, or at least cloud computing. So you will see how cloud computing platforms use virtualization. So we are going to start with what virtualization is, how it works, and so on. And then we will see how it is used in systems like data centers and cloud and things like that. Okay. So let's start with the definition of virtualization. What is it? Okay. So here's a very simple definition, and we'll see how it is actually instantiated in practice. So virtualization essentially means you extend or replace an existing interface to mimic the behavior of another system. Okay. So essentially it's a layer of software typically that takes one interface and uses it to emulate a second interface. A very simple definition, and we'll see how it's intended. So here is an example. Okay. So let's say this is machine A. Okay. It basically runs hardware and software system in. That's an Intel architecture, it runs Linux. Yeah. And it exposes an interface. At this point, the interface is, let's say, the Linux API, the system call API that Linux is going to export. And if you have no virtualization, all applications that run on this machine essentially have to use that interface to run. You have to use the system calls or libraries that are presented on the machine that actually use the system calls. Okay. So that's not a virtualized one, that's just sort of the native environment. Here is an example of virtualization. Okay. Here we assume that you actually have a different hardware and a different piece of software. So this is machine B that runs hardware or software of type B. Okay. That essentially exports interface B. Okay. That's native to that machine. Now, if you actually have a layer on top that uses interface B to mimic interface A, that we will refer to as virtualization. Because we said virtualization essentially uses an existing interface to mimic a second interface. Okay, so here you are using interface B, and then you have written a piece of software that emulates interface A using interface B. At this point, it's very abstract, so let me try to make that more concrete. So let's assume software system B is Windows. Okay. So the interface B is the Windows API, Win32, Win64 API. Okay. Clearly, if you have a Linux process, it's not going to just run on Windows. It was compiled for Linux. It's going to use the Linux APIs. Okay. Now, if you actually have a piece of software that runs on Windows that exposes the Linux API, you have re-implemented the Linux API using the Windows API. You are emulating Linux on top of Windows. Okay. Then you could run a process that was designed to run on this environment, essentially on that environment, because it is going to use interface A. This virtualization layer has exported interface A, although its native interface is Windows. We are exporting a Linux interface. So then this Linux process is going to run on this environment. Okay, so virtualization has allowed you to expose a second interface using the first. Okay. Now let's look at a little bit of history. Why does this all make sense? We'll talk about in just a moment. Okay. The virtualization was introduced, I think, in the late 60s, early 70s. The old technology, almost 30 or so more years old at this moment. It was designed by IBM. And the reason it came about was the following. So IBM used to be a mainframe vendor. It still is, but it does a lot more things than mainframe. So those days, companies would spend, let's say, $1 million to buy a mainframe machine. Okay? Then they would run all of their applications on that mainframe, whether it is running payroll systems or whatever else that may be, you run it on that mainframe. Right? Let's say you write a lot of code, write your applications on that mainframe. Okay? 3, 4, 5 years down the road, machine becomes old. You basically have to go and buy another mainframe. It's time to replace it with something newer because that machine is old, it's too slow and so on. Okay, so you go back, let's say you go back to IBM, say machine is old, I need to buy a new one. They'll say, yes, we have a much better machine, it's much faster, it does everything better than your old machine, still costs $1 million, and by the way, we changed the processor, we changed the operating system, so none of your code is going to run. Okay, so you can pay $1 million, but you have to rewrite all of your application. Okay. Now, there were not too many vendors in those days, I mean, only very few who built any kind of mainframes, even today there are only a few. So you don't have much choice. Right? So you have to go and spend your money, but you don't want to go and rewrite all of the code. You may have spent years developing application. You can't just throw it out and say, these guys just came up with a new processor architecture that is not at all compatible, new instruction set, that we did the OS, now this new OS and it doesn't run anything. There has to be a way to make it work. Yeah. So basically, clearly, you cannot really tell your customer if you're, even if you're IBM or any other vendor for that matter, saying, buy my machine, it's faster, but nothing that you do right now is going to work. Okay, so what they did is, because they came up with either a new hardware architecture or a new OS platform, they said, we will give you a layer. Okay, it's an emulation layer. That layer will emulate the old hardware. Okay, so any code that you have written will still continue to run. Will run in emulation mode. Okay, basically, you run it on top of this layer of software we have written. That software presents the old, it basically makes it look like it's still, the code is still running on the old machine. It's going to emulate the old processor, old API, all of that. So all your old code will run, and if you write new code, write it to the new platform. That way it will actually take advantage of the new functionality you put on that platform. Okay? So they were clever enough to realize you can't just change everything and sell it to your customers and expect that they will be happy. They said, here is the solution. We have this new hardware, it's faster. It will run everything that you run today. And if you write new applications, you can make it even better because we have all these extra features in our new OS, okay, which is not compatible with the old OS, but then for new applications, that's okay. Okay? So they essentially invented this notion of virtualization to do exactly that. So software system B is the new hardware or the new operating system that runs on the hardware. Okay, the virtualization layer is essentially mimicking the old hardware and the old operating system, okay, which may be completely incompatible. It could be completely different processor, okay, not at all backward compatible or anything like that. Okay? So that's how it was designed in those days, and today it's used for much more than that. Okay? But that's the quick history into what is virtualization and what it does for us. Okay? So our basic takeaway is to know what the definition is. It's the ability to implement one interface on top of another. Okay? Any questions on this before we actually jump into lots of details? Is it clear what is virtualization? What's the definition? Okay. So if you actually dig deeper, you will see that there are many types of virtualization. What I just explained was a very abstract notion. I said you use one interface to mimic another. I didn't actually say what that interface was. I gave some examples, okay, but those examples are not necessarily going to cover all the case. So you can implement virtualization at different levels of your hardware and software stack depending on what interface you are trying to mimic. Okay? You can have hardware level virtualization, that's the lowest level of virtualization, where you are mimicking one processor using another processor. So you can mimic an entire instruction set in emulation. You may be running on an Intel machine. Okay? I can write a piece of software that emulates a software processor. Okay? It would be completely different. It could be Spark, it could be ARM, it could be any other processor. Okay? So any programs that are designed to run on that processor will run on emulation. That's hardware level virtualization. Okay? You can also look at the interface that the OS exposes and mimic some other OS. So this is OS level virtualization. So what I was talking about of running Linux on Windows essentially is OS level virtualization. It is exposing the Windows API, the Linux API using the Windows API. You're using one system called interface to mimic another system called interface. Okay, if you've heard of Wine, anybody here heard of Wine? Okay, Wine essentially does OS level virtualization. It is implementing the Win32 API on another platform. Okay, the Win32 system calls are being implemented. That's a form of virtualization. Okay, there are many other examples that you will see. So that's OS level. Okay. You can have library level virtualization. You can use one library interface to emulate another library interface. That is application level virtualization. Okay, Java virtual machine, JVM, is application level virtualization. Okay, JVM may be written in C. So using C libraries to expose a Java interface. Okay, one library is being used to emulate another. So you can do virtualization at different levels in the stack. And depending on where you do it, you get OS level hardware virtualization, OS level virtualization, application level virtualization. We are going to look at all of these. You may not have, you may have encountered some of these already without realizing. Others you may not. So depending on what is replaced or mimicked, we get different forms of virtualization. Okay. So I'm going to run through a few, whatever I just talked about, in a little more detail. Then we are going to look at some of this in a lot more detail. Okay. The first one is hardware level virtualization. This is also referred to as emulation. Okay. Typically, this is used to emulate one hardware on another. Okay. So the virtual machine or the virtualization layer emulates a complete piece of hardware. You can emulate an entire machine. You can emulate an entire PC in software. Okay, all of the processor, the memory, the disk, the network, everything you can emulate in software. You can write a program that makes it look to another program that's running on top as if you are running on a software PC. Okay? So you can then, if you do that, you can run an unmodified guest OS on a different PC. If you heard of Box, that's a very popular open source emulation environment. It allows you to emulate support lots of different processors. Okay? So you can emulate one processor on top of another. Okay? At one point when Macs used to be actually PowerPC based, okay? You had this piece of software built by Microsoft actually called Virtual PC for the Mac. Okay? Because in those days Macs were based on the PowerPC architecture. They couldn't run Intel based applications. So Microsoft had this virtualization layer called Virtual PC that emulated an entire x86 machine. It's x86 PC on your PowerPC architecture. Okay, then you could run inside that. You could run Windows or Linux or anything that was designed to run on a PC. You could run on a virtual PC, okay, which was essentially running on some other machine. QEMU is another emulation environment that is also very popular, used in the Linux world and so on. That also does full emulation. Okay? Now the advantage of doing emulation is you can essentially emulate any architecture you want, any hardware you want. Okay? Because you're implementing the entire sort of functionality of the hardware in software. Okay? Now what are some disadvantages of doing this?
It will become slow and each machine instruction will be
okay, might be slow.
Yeah, I was gonna say it's very
It is going to be very slow, okay, because what happens is the programs that run in emulation mode, they are going to execute assembly instructions on the emulated environment. Each assembly instruction has to be replaced by one or more instructions on the native environment. Okay, you have to do dynamic translation. You have to translate and execute. Okay, it's going to be significantly slow. Sometimes you get an order of magnitude slow down, okay, in your execution, but you can run old applications or applications designed for another environment will run. They'll just run slow because you're doing native instruction by instruction translation and execution. Okay. That's emulation. Okay. Next form of virtualization is essentially what is called native or full virtualization. Okay. So in this case, basically the difference is, in this case, what you're doing, let me go back 2 slides. What you're doing is you're essentially the interface A that you're emulating is the same as interface B. Okay, you're emulating the same interface using the underlying interface. Okay, in emulation, I said you can take one interface B and you emulate a second interface A, which is different. You can emulate a virtual PC on a power processor. And now, if you happen to emulate, if A and B are the same, if you're emulating the same interface using the underlying interface, you basically get native virtualization. Okay, so you could ask, why would you do that? Why do you want to take one interface and write a piece of software that emulates the same interface again?
You can easily migrate the virtual machine to another computer.
You can migrate, but we haven't even gotten that far. You're jumping maybe 3 steps ahead of where we are. I'm just asking, what is the rationale to say that I'm going to write a piece of software that basically takes one layer and exposes essentially the same layer above it?
You can run it as a separate application, so even if it crashes, you just crash that application and not the entire system.
Okay, so you can run it as a separate application inside the virtual machine, and if you want to basically isolate it from crashes, etc., you can do it. That's one possibility, and definitely valid possibility. Any other ideas on this? So think of, I'm emulating x86 on x86. I'm emulating Intel on Intel. The most common case of actually full or native virtualization. Where would you use something like that?
something in native environment like Linux and Windows both run on x86.
Okay, that's a good observation. Okay, so even though you may be emulating the same hardware, there may be many different operating systems that run on that hardware. So I could run Linux on Windows. I could run Windows on Linux. Both run x86, but typically if I'm running Windows, I cannot run Linux unless I do dual boot or some such thing. Okay. So that's actually a very common case of I'm emulating the same hardware. So I'm emulating an Intel PC in software on another Intel PC. Okay. But on that emulated Intel PC, I can run a second operating system. I can actually run Linux on that operating system. And then, so then I can run Linux app on my Windows PC, or I can run Linux app on my Mac PC. I can show you that you can actually do this with many popular virtualization platforms like VMware. Okay. So this is basically native virtualization. Now the advantage of native virtualization is because the hardware family is the same. Okay. You don't need to do full translation. The assembly instructions, whether you do have Linux or Windows, are going to be the same. They are actually for x86. Okay. You have to basically simulate enough pieces of hardware, but once you have done all of the rest, you don't actually have to do any translation of assembly instructions. The assembly instructions map one to one. An add assembly instruction in Linux is an add assembly instruction in Windows because it's actually an x86 instruction. It has nothing to do with the platform. Okay. So in this case, although there is going to be a slowdown or overhead to pay because of the virtualization layer, the code is not going to see the same level of slowdown you see here. Because for here, every assembly instruction has to be replaced by one or more native instructions. Here you don't have to do that. Okay. But you have to still simulate all of the rest. I mean, Windows won't just run out of the box on Linux and things like that. So other pieces do have to be emulated. But the instruction sets don't need to be translated. Okay, so the slowdown or the overhead you see is actually much lower in this case. Anyone here use VMware Parallels or anything like that? VirtualBox. Okay, so lots of you have used it. So you should have said why you should emulate the same hardware of another hardware because you know what the use cases are. Okay, I'll show you at the end of the class an example demo. Okay. So the third form of virtualization is called para-virtualization. Okay. In this case, what happens is the virtual machine or the virtualization layer doesn't actually simulate the hardware. Okay. What you do instead is you go and modify the guest operating system and add some extra calls in the guest operating system so that it runs on another OS. Okay. So you still want the same scenario. You want to able to run one operating system on top of another operating system. Okay. In case of native virtualization, that operating system was unmodified. It could run out of the box. You have to make no changes. You just show up with an installation disk or an install image, and you can install it inside the virtual machine. It would just run. Okay. In para-virtualized world, okay, you are basically going to take some shortcuts. You are going to say that I'm going to basically modify the flexibility of modifying the OS and making some small changes. Then I'm going to be in what is called para-virtualized mode. So what happens in this case is the virtualization layer is referred to typically as the hypervisor. Okay. Hypervisor is going to trap calls from the operating system and execute those calls. Yeah, simply because let's say Linux is going to make some Linux apps are going to make Linux system calls. The Linux kernel is going to try to execute those system calls. If Linux is running on top of Windows, you'll see that it doesn't actually have enough privileges to execute it. It will cause the machine to crash. Okay. So you want some ability for one OS to actually run on top of another OS. That is essentially done in para-virtualized world by modifying the OS. Okay. In native virtualization, you use other tricks, and we'll see what those tricks are to make that work. Okay. Zen is an example of this environment, the Zen hypervisor. VMware has some other products like ESX server that also use para-virtualization. And we'll go into some details of exactly what is being modified and why it's being modified in a few slides. But let me continue. Next form of virtualization, as I said, is OS level virtualization. Okay. This basically says that not only the hardware is the same, okay, the OS that runs on top of that OS is also the same. So I'm going to run Linux on Linux. In the previous case, I said I'm running x86 PC on an x86 PC. Now I'm going to say I'm going to run Linux on Linux. Okay? But then the Linux that's running on top is isolated from other Linux instances that are running. Okay? So if you heard of Solaris container, BSD jails, or Linux vServers, that's allowing you to construct an isolated container that presents a full-fledged Linux environment that runs on another Linux environment. The reason to do this is you can essentially run untrusted code inside that container that looks to that code as if it's running on Linux, but it's isolated from everything else. Okay. So you have basically Linux, let's say x86, and you can create what is called a container. Solaris, that it's actually called a container. Let's just use the word container. So this looks like a tiny Linux OS that runs on top, and an app runs here. Okay, this app cannot actually see other apps that are running on that OS. Neither can these apps see this app. Okay, they are isolated from one another. Okay, so if this app does something malicious or is buggy and crashes or anything like that, these other apps are unaffected by it. Okay, so this is often used for either performance or security isolation. Okay, so that's the use case for emulating Linux on Linux in this case, or Solaris on Solaris or Linux. So it's basically a way to isolate whatever is running in that container from everything else. But the process that's running in the container just sees an ordinary, the same OS as the native OS. Everything looks the same. You just cannot see what's outside. So in BSD, this is called a jail. Yeah, so you essentially jailed that process, so it cannot see anything else. It cannot harm anybody else or anything like that. So you isolated it using OS level isolation mechanisms. Okay. Another form of virtualization. Yes, sir.
How does it help performance? Either it helps with performance or it helps with performance.
Okay, so question is, I said it helps with performance. I did not say it improves performance. I said it's performance isolation. Performance isolation essentially means that if this code is buggy, let's say it hangs or goes into some sort of an infinite loop, okay, it is not going to chew up all the cycles that are allocated here. So you can restrict, saying this jail or this container gets 512 megabytes of RAM. It gets, let's say, X% of the CPU. Okay, so you can assign resources to a container. Okay? So then that container can never take more than that many resources regardless of what's happening. So if this machine, if the app goes haywire and just starts chewing up CPU cycles, though it will be restricted to that limit that you enforce on that container. You cannot then harm other applications. Otherwise, if you have a process that hangs on your machine, it can hang the entire machine. So here that cannot happen.
This is layer on resources in virtualization.
Sorry,
right?
what's the question?
Because like, you don't actually run a kernel in every container.
Yes.
So at least like the memory difference.
Yes, it's a good question. So what is being pointed out is you are not running an entire copy of Linux in this container. This is just a way to isolate. In para-virtualization, you are actually running one OS on top of another OS. Here, this OS has provided you a feature by which you can carve out a piece of that machine, some amount of resources, and allocate it to a container. You are not actually running a new OS in that container. This OS continues to service all of the requests. So this app is actually seeing the native OS, okay, except that it's been restricted in the amount of resources you can use. Okay? Yes.
Question. Is this just another name for sandboxes?
Yes, sandboxing is an example of this OS level container. Now I should mention one small difference is in Solaris, you also have the ability to expose different kernel versions. Okay, Solaris, you can tell Solaris saying, make it look to the process as if you are an older version of the kernel and old version. So here, you could create a container that say, let's say you're running Linux 3.x kernel, okay, which is sort of the latest kernel. But you have some code that only works on Linux 2.6. Okay? So you can create a container and say that make it look like this is a Linux 2.6 container. Okay? So what the underlying OS will do is it's backward compatible. So to this container, it will only expose old versions of the system call. So it has compatibility built in. It has multiple versions of the API built in. Okay? That's the only difference. So you don't have to actually run an entire OS, but you can expose other interfaces. That's what we said. You can mimic one interface using another. So you can mimic the same interface, or you can mimic an older interface. Okay? So this is a way to do sandboxing, is performance isolation. This is a way to also ensure backward compatibility. Okay? So Solaris introduced containers for backward compatibility reasons as well. Same thing that IBM did. Okay? Solaris said we have now new version of the OS. If you have code that only runs on old, create a container. In the container, set the OS version to be the older version, and code will run unmodified, because the new version can emulate the old system calls. It can also run the new system calls. Okay. Okay. So last type of virtualization, application level. Okay. There are many examples of this. So you are using one library to implement another library. Simplest example to think of is the JVM, the Java Virtual Machine. Code is written to using the native libraries on that machine, but it emulates a Java interface. That's the interface we expose. Many other similar environments. So if you actually heard of this thing called Rosetta on the Mac, what that did was essentially was application level virtualization. It allowed at application level for a library to emulate PowerPC. Okay, if you have followed this history of a Mac, you will know that a few years ago, Macs were switched from PowerPC to Intel. And now Mac is essentially running on an Intel processor. But when the switch was made, basically they changed the processor. Okay, so they had to deal with the same problem. If you're a user, you purchased lots of applications, or you're running lots of applications that run on PowerPC, none of that code will work anymore, because the hardware has been switched to a different processor family. Okay. So they implemented this emulation layer called Rosetta, okay, which was essentially doing dynamic binary translation. You could run an entire PowerPC application. So you could take an application, you could double click on it. It was compiled for PowerPC. What would happen is the OS would recognize that this is a PowerPC compiled binary. It would attach dynamically a library to that binary. And whenever what that library would do is it will intercept every instruction. PowerPC instruction, it will on the fly translate it and then execute it natively. Okay? So it is doing what emulation environment is doing, except that it did not actually expose an entire processor. It was just a library that was taking every call and on the fly translating. So to the user, this was completely transparent. You could take all of your application and you could actually run that, and you wouldn't even know all that translation is happening. It was totally transparent. You would just start it up, and the underlying machine would actually figure out, is this x86 or, so they used to call it, they also had this thing called universal binaries. So the binary would you could construct it with PowerPC code or x86 code, so it would run on both. Okay. You could have native binaries that could be translated also. So they had all these emulation features built in. Okay. Wine is another example here where we are basically doing. It's not quite application level virtualization. It also uses emulation a little bit, but for all practical purposes, you are implementing Win32 libraries on top of Linux. So you can run, let's say, Internet Explorer on your Linux machine or things like that. Any questions on this before we jump into more details of some of these techniques? Okay, so this is just a quick overview of virtualization at different layers. And now we are going to go back and talk about this layer in particular. I'm not going to spend too much time talking about emulation. We'll talk about native virtualization, and we'll talk about para-virtualization. Okay, so two types of virtualization, and then at the end we'll talk a little bit about application layer. Okay. So here is a slide that shows two pictures. Okay, so both are examples of hypervisors that do native virtualization. Okay. They do slightly different things. Okay. There are these hypervisors are called type 1 and type 2. Okay, very poorly chosen names, but they are meaningless. Okay, so type 1 virtualization essentially says that the virtual machine software, which we'll call the hypervisor, runs on bare metal. Okay? The machine, boot the machine up with the hypervisor, not with an operating system. Okay. And then on top of that hypervisor, you can create virtual machines. That virtual machine is going to emulate the same architecture. As I said, this is x86 on x86 environment. You're emulating the same interface on another interface. Okay, so here you have virtual machine 1 that emulates the same underlying hardware. You run Windows on that inside that virtual machine. The virtual machine 2, that says that's the same emulation, you run Linux and so on. So you can have multiple virtual machines running, each running a different operating system, okay, and then you have processes that run on top of that operating system. Here you have Word, there you have some other Linux application and so on. Okay. This is referred to as bare metal, okay, hypervisors. So typically you only see this in server worlds. Unless you're doing research in this area or you have actually worked in a data center, you will not see this type of hypervisor because they are used in server environments. Okay. If you have used VMware or Parallels or anything like that, you typically would have used what is called a Type 2 hypervisor. So in this case, your machine runs some native operating system. It could be running Windows or Linux or a Mac OS X. Okay. On that operating system, you run an application, which is actually a hypervisor. Okay. That's a Type 2 hypervisor. This hypervisor also emulates the same underlying hardware. It emulates, let's say, a software PC on top of another PC. Okay. So it's exposing a PC interface in this case, if it's VMware or some such thing. And then in there you can create a virtual machine that's a guest OS. Okay. So you run a second operating system here, which could be different from the first operating system. Okay. And then inside that operating system you can run whatever applications you want. So this allows you to run, as I said, Windows on Mac or Linux on another platform and so on. So that environment is referred to as a Type 2 environment. Okay, so I can show a very quick example if I can get it to quickly run. Okay, so I have here two. So here I have two virtual machines created. Okay, so this is actually the hypervisor interface that you're seeing. This is VMware Fusion that's running here, and I have loaded Ubuntu. So this is the Mac. So you can actually start it at some point. So the machine is starting up at the moment. Let's start. Okay, so this is an example of running a Type 2 hypervisor, which is in this case VMware. There's a virtual machine that's running on a Type 2 hypervisor. That virtual machine is a software PC, and that software PC I have Linux running. This is an example of Linux running on a Mac OS X. Okay, for those of you who haven't seen what a virtual machine does, this is basically Ubuntu, which is you could create as many virtual machines as you want. Okay, so here is now Firefox running on. Okay, so it's going to take a while to start up. When it starts up, it's a bit slow. So here you have basically all your Linux apps, you have OpenOffice and so on. There is Firefox that's running inside Linux. Linux is running on OS X. Okay. Now OS X doesn't know, it's a it's a host operating system, it doesn't know. So this entire virtual machine looks to the underlying operating system as one process. Okay, it doesn't. So inside this Linux, you may have tens of processes. None of that is visible outside. Okay, so if you actually look at what is happening inside here, so if you see. So here is that VMware Fusion that's running. You'll see that it just looks like a single process. Inside that process is running an entire operating system, and inside that OS is running lots of processes. None of that is visible outside. It is all because it's emulated by VMware. It's all handled at that level. So you can't see anything that's running inside your host, inside your guest rather from the host. Okay, that's just a very quick digression into how it works. Okay, so that's Type 2. The same kind of thing is going to be true in type 1. And you could, I only showed you one virtual machine running, I could have started a second one. Okay, then you would have two operating systems running on top of host operating system both at once. So you can have as many of these as you want, provided you have enough memory and CPU and so on. Okay? Yes, question.
Is there a difference between the sort of functionality exported by type 1 network and type 2 hypervisor? Things are very common.
Okay. Question, is there a difference in the type of functionality exported by type 1 and type 2? There's no difference in the functionality that's exported. Both export, in this case, they will export an x86 machine, so you can run a guest OS. There's a big difference in how they're implemented, and we look at that difference. What they expose to any guest is the same. How they work is very different, because in this case, there is no OS. This is the OS. This is what boots up on the machine. In this case, you boot up your normal operating system, then you just start an application, it just happens to be a hypervisor. Okay. So they have to be implemented very differently, because here this hypervisor can leverage an OS that can do a lot of its tasks for you. Here, there is no such thing. The hypervisor has to do everything. So it has to enable all this functionality. Okay. So we'll talk a little bit about how virtualization works. I'm going to explain this somewhat in the abstract first, and then we will go into and understand the details of how this works. Okay, so here is where you need to know a little bit about how processor works and how typically operating systems have been written and so on. Okay? So if you know anything about hardware architectures and processors, you know that there are this notion of protection levels or rings. Okay, there's something in x86 called ring 0, ring 1, ring 2, ring 3. These rings essentially define levels of protection, or what privileges a process has if it runs at that level. Okay? Typically, the OS kernel runs in ring 0, which means that it has full control over anything that's happening on the machine. Okay? User processes run at ring 3, which means that they can only run some instructions, but not special instructions that only the kernel can run. Okay? And this is left for protection. If you let a user process, do whatever it feels like, it is going to go corrupt something and then bring the machine down. So certain things you only trust the OS to do. You don't let processes do. Okay? This is implemented at the hardware level in the form of protection rings. Okay? Basic architecture 101 concept, but it's something you should keep in mind. Okay? So kernels will run at sort of the lower, basically no protection at all. It runs in ring 0, processes run in ring 3. Something to keep in mind, we'll come back to that. Now, if you take the instruction sets on any CPU, you can partition them into basically what are called instructions that only the kernel is allowed to run, and other instructions that any process can run, including the kernel. Okay? The ones that only the kernel is allowed to run are referred to as sensitive instructions. Okay? So these are instructions that can change page table settings, for instance. Because there are page table hardware on the machine and so on. Only the kernel is allowed to make those changes. There are instructions that trigger I/O. Yeah, if you know anything about operating system, all I/O at the lowest level, all I/O to the hardware is only done by the kernel. Okay? Typically, a process is going to invoke a system call, a read or write, and you let the kernel actually execute or do the I/O. Okay? So I/O is sensitive. Changing page table settings is sensitive. So these are instructions, specific assembly instructions that you only allow the kernel to do. Nobody else can do. So process tries to do it, it will not be allowed to do it. Process, user process. Okay. That's one concept. Second concept is basically what is called privileged instructions. Okay. So these are instructions that also cause a trap. Privileged instructions are simply instructions that cause a trap, or you think of a trap as an interrupt. Okay, any instruction that assembly instruction that you have in your architecture, on your processor, that causes a trap is referred to as a privileged instruction. Okay. And the claim is, and I'll explain why that is true in just a moment. The claim is you can implement type 1 virtualization, okay, on some platform only if sensitive instructions are a subset of the privileged instruction. Okay. Only if the sensitive instructions are also the ones that cause a trap. Only in that scenario is it even possible to implement type 1 virtualization on a piece of hardware. And I'll explain why all of this is true. Okay, so let's assume that you are running a guest operating system. And basically, let's say you're running Linux, there's a process that's done a system call that comes to the Linux guest. Linux guest tries to implement an IO or MMU or whatever it is, but it's not actually running on the native hardware, it's running inside a virtual machine. Okay? So typically, in this case, the guest OS has the same privileges as a user process. It doesn't have the same privileges as the underlying host operating system. So it will not be allowed to do certain things because it's not the real kernel. Okay? So in this case, this OS has the same privileges as any user process. It's no more distinguished. So it cannot do things that it would normally be able to do if it was running on native hardware. So this guest OS is running in ring 0, ring 3. This is the only thing that you trust here. Okay? But the question is, how is that guest operating system going to do all of the things that it would normally do if it was running directly on hardware? And this is where I think some of these things come into play. So I'll explain what this is in the next slide using an example. So what happens in x86, or at least in 386, is sensitive instructions that are actually executed by user mode are essentially ignored. Okay, if a user process tries to do any of these things, the architecture simply ignores it, saying you have no privileges, so I'm going to ignore this instruction altogether if you try to execute it. Okay. If you ignore it and don't cause a trap, then there is no way for you to actually implement virtualization of this. And we'll see that on the next slide as well. And the way they have tried to address this is now today's Intel AMD CPUs have extra support. So what they have done is they have this thing called Intel VT, or AMD has this thing called SVM. If you turn on VT support on your processor or SVM support on your AMD processor, you will actually have a bitmap that tells you for these instructions also trigger a trap if those instructions are executed in user mode. Okay? And if you do that, then we can see why you will be able to actually implement virtualization, and that will be clear using the following example. Yeah, so here is our type 1 hypervisor. Okay? This is hardware. Okay? That's the hypervisor that's running there. That's the operating system that's running on top of that hypervisor. Processes run inside the virtual machine. Okay? The only thing that is trusted on this hardware is the hypervisor. The hypervisor runs in ring 0. It has full privileges. Okay? All virtual machines run in ring 3. Or some lower levels of trust. So in particular, this guest operating system is not allowed to directly do IO. It's not allowed to directly muck around with hardware page tables because it's not trusted. It doesn't have enough privileges to do it. Only the hypervisor has enough privileges to do it. Okay. So now let's take a user process inside that virtual machine that simply wants to open a file, okay, on disk. That's IO. Yeah, so it's going to make a system call, or maybe it calls some library function, print scanf or whatever, or fopen or some such thing, and that will trigger a system call to the Linux operating system that's running there. Now, the Linux operating system will assume that it's the kernel, so it has full privileges, and it will try to open a file on the underlying disk. But because it doesn't have full privileges, this will not actually work. Because if there was no hypervisor here, it was directly running on hardware, that would have worked because that runs with full privileges, so you can actually access hardware. But in this case, you are not able to access hardware. So you have to basically somehow tell the hypervisor to now do it for you. Okay? The process requests the kernel. The kernel has to tell the hypervisor saying, can you do this for me? Because I don't have privileges, you do it for me. So you have the right privileges to do it. So you have, the guest OS has to somehow tell the hypervisor to execute that privileged instruction for it, or sensitive instruction for it. So how do you do that? You have to basically be able to signal the hypervisor. Yeah, how will you signal? You will have to raise an interrupt. Yes, I want to do something, here's an interrupt, then you'll go into interrupt service routine, and the hypervisor will actually do whatever you're asking it to do and return back to you. Right? So this is basically where this result comes in. So if sensitive instructions are also the ones that raise an interrupt, then you can implement type 1 virtualization, because what would then happen is it's all transparent. Okay? You basically make a system call from the process, it comes to the kernel tries to execute something that is sensitive, tries to change some page tables or tries to do something, some IO. Okay? It doesn't have privileges, but these instructions also raise a trap, because I said sensitive instructions are privileged, they will raise a trap. This trap will cause the hypervisor to run. The hypervisor will say this guest OS wants to do something that it doesn't have privileges for, and it will execute it for it and then return back. Okay, that's sort of the arrow shown here. The guest operating system basically causes a trap by doing something privileged. This is type 1 hypervisor is actually running in kernel mode. That kernel, although it's a kernel, is actually running in user mode. And then it will trap here, it will execute and return. Okay, this is basically how virtualization is going to work. Okay, you don't actually trust these guest operating systems. The only thing that is trusted is the hypervisor. So the guest operating system, every time they have to do something that needs higher privileges, you have to signal the hypervisor saying do it for me. Just as processes are not trusted by the OS, the processes tell the OS to do something. Okay? In this case, the OS essentially tells the hypervisor to do something. There are multiple levels of trust here. The processes are not trusted by the OS, the guest OSs are not trusted by the hypervisor. So each has to tell the next layer, the layer underneath, saying go do this for me. Okay, that clear? So basically, so unmodified OS is essentially running in user mode. It doesn't know. Okay, that guest operating system is unmodified. It doesn't know that it's running on inside a virtual machine. It thinks it's running in kernel mode. So it is going to merrily go and start executing all of these things that the process is asking to do. But thankfully, because those instructions also cause a trap, they come to the hypervisor, and the hypervisor is the real kernel here. That's the one that's actually going to execute it on your behalf. Okay, so upon trap, execute privilege instruction or emulate. Okay, you can either actually execute or emulate the impact of making those calls. All right? Any questions on this? So this is basically the guts of what is happening inside your virtualization. It's very important that you understand what rings of protections are, okay, essentially how kernels and user processes work. That there are two types of instructions, some things that only trusted entities do and some things that processes can do, and how the entire chain works, and then how virtualization is made. Okay, so I will stop here. We ran out of time. Next time I'll talk a little bit about how the same functionality is implemented in type 2 hypervisor.